Okay, let's talk molecular orbital diagrams. We're going to calculate bond orders based on molecular electron configurations. We will write molecular electron configurations for first and second row diatomic molecules, and we'll relate electron configurations to the molecule's stability and magnetic properties. Molecular orbitals are the combination of two atomic orbitals from different atoms. So we'll start by reviewing atomic orbital filling diagrams and then go on to molecular orbital filling diagrams. So we fill the orbitals following these three rules. The off-bow principle, which says that we'll fill the lower energies first. The Hund's rule, which says that we have to fill the degenerate orbitals with one electron in each orbital and then go back and pair them. And the Pauli exclusion principle, which says that no two electrons may have the same exact quantum number. So we have one spin up and one spin down in each box. In this particular example of silicon, we increase the energy as we go down, mainly because I did it with tables. Anyway, a more accurate representation based on energy would probably look like this. So we'd have a box for the 1s, and then like up here we'd have 2s, and then above that 2p, and we'd have 3s above that, and all the way up there 3p. This gives us increasing energy as we go up, which most of us prefer. Now let's look at a simple molecular orbital diagram. The simplest case for describing this theory is a homonuclear diatomic molecule. Homo means same, nuclear means nucleus, di means two, and atomic means atoms. So in other words, things like hydrogen gas, nitrogen gas, fluorine gas, etc. We're going to illustrate this concept with the simplest case, hydrogen, the gas. So we represent the contributing atomic orbitals on the left and right, and we combine them together to create the molecular orbitals in the middle. So in this case, we have two 1s electrons in hydrogen to start. They combine to form one bonding and one antibonding orbital. Two orbitals in, two orbitals out, two atomic orbitals in, two molecular orbitals out. Okay, the bonding orbital is lower energy than the original orbitals, and the antibonding orbital is higher energy than the contributing orbitals. Together, they add up to the same energy as the original orbitals. We will fill the molecular orbitals using the off-bow principle. So we go from low to high. We put one spin up and one spin down because of the Pauli exclusion principle. So we have the bonding orbital filled. Now, there is a concept that helps us decide whether or not bonding will happen called bond order. Bond order is given by the number of bonding electrons minus the number of antibonding electrons over 2. So for hydrogen, we have 2, 1, 2, count them, bonding electrons. We have 0 antibonding electrons. We put that over 2, and our bond order is 1. This thing will bond. It will do the thing. The concept of bond order can also be used with Lewis structures, where a single bond has a bond order of 1, double bond order of 2, etc. But it's not very predictive. As bond order increases, the strength of the bond increases. If the bond order is 0, then a stable bond cannot form. Okay, so in this case, bond order is 1, the bond will form, and it's reasonably stable. Let's do an example where we can't form the bond. Here we have He2. There are 2 bonding electrons in each of our atomic orbitals. When we combine that into our bonding and antibonding and we fill it, we have 2 electrons in bonding and 2 electrons in antibonding. So if we do the bond order, we get 2 minus 2 over 2, which is equal to 0. When bond order is equal to 0, it will not bond. This squares with experience. Helium is a noble gas. It doesn't bond with other molecules. It's not going to happen. Therefore, the bond order will always come out as 0. Let's look at only the molecular orbital energy levels and compare them across the second period. So we have lithium through neon represented here. Beryllium, Be2, and neon, Ne2, do not exist. They will have a bond order of 0 if we do the orbital filling. This is an accurate representation of energy levels in these molecules. When the bonding and antibonding orbitals split, we end up every single time with the sigma 2s and the sigma 2s star being the lowest energy orbitals. Now, as we go up in energy, you can see that we have this one orbital that flips order. So let's talk about that flip. As we match pi orbitals up, our sigma is going to be higher energy than the degenerate Py and Pz for lithium through nitrogen. So we go pi to Py, pi to Pz, and then we go up to sigma to Px, and then above that is the pi to Py star and the pi to Pz star. And at the very highest, we have the pi to Px star. Now, for oxygen and fluorine, because again, neon is not going to bond, the order is sigma 2s, sigma star 2s, sigma 2px, pi 2py, pi 2pz, pi 2py star, pi 2pz star, and then at the very top, sigma 2px star. So what causes this switcheroo? Well, in this case, it's sp mixing. We'll get more into that in the next slide. These orders are important because these orders will help us to determine magnetism, which is going to be the next subject about these things. Know these orders because it will be on the test. All right, so here we have a more clearly defined visual of sp mixing. When sp mixing happens, the split in energies is far greater than when it doesn't. So we can see that we have a greater energy level difference on the left than we do on the right. What is going on here? Actually, all of them, as we go across the second period, have sp mixing, but they have a greater effect when the S and P levels are close in energy, as they are in lithium, beryllium, carbon, and nitrogen, but not so much in oxygen or fluorine, or neon, if that actually bonded. So hopefully this gives you an idea of what is going on here. Now, let's get some practice. I'd like you to draw the molecular orbital diagram for oxygen. And remember to fill your molecular orbitals using off-bell principle, Hund's rule, and the Pauli exclusion principle. So take a pause and do the thing. Hopefully, this is what you got for your solution. And you'll notice that there's an interesting thing in this solution. So we follow the off-bell principle, Hund's rule, and Pauli exclusion principle. Since oxygen has 6 valence electrons, which you show in the atomic diagrams to either side of the molecular orbitals, when we go to fill the molecular orbitals, oxygen has sp mixing, and we end up with this order for our filling. And when you fill those orbitals, according to the rules on the right, you end up with 2, count them 2, unpaired electrons. This is a crucial result for explaining the magnetic properties of oxygen. We're going to take a little segue to learn about the magnetic properties, and then we'll discuss this a bit more. Magnetism can be measured using a Gouy balance. I'm sure I'm butchering that explanation, but we're going to go with it. It's represented in this picture on the right. So if we place a sample in a magnetic field, it will get heavier if it's attracted to the field and lighter if it repels the field. So what are we talking about this? Ferromagnetic materials are permanent magnets. They have unpaired electrons. So unpaired electrons, if they're all spin up, they can align in a magnetic field and then be attracted to the field. They're always aligned in iron, nickel, cobalt, and gadolinium. So when you make alloys containing those elements, you can also have ferromagnetic materials. All of them will be heavier on a Gouy balance. In fact, they may be just like swinging over to one side versus the other when it's ferromagnetic, depending on quantity. Paramagnetic materials are attracted to magnetic fields. They have unpaired electrons. They may be ferromagnets at lower temperatures, and they are heavier on the Gouy balance. Diamagnetic materials weakly repel magnetic fields, so paired electrons are in there. They cannot align in a magnetic field, so they repel the field. They are lighter on a Gouy balance. Getting back to what we were talking about with oxygen. Valence bond theory showed oxygen with all paired electrons, like we had 2 lone pairs on that sucker when we put it together on both sides, right? So I'll go ahead and draw that. You would have from your Lewis diagram 4 unpaired electrons on the entire molecule. Boom, 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 boom. That does not predict any paramagnetic behavior. It would in fact predict diamagnetic behavior, but that is not what actually happens. Oxygen is attracted to magnetic fields. It's paramagnetic. The unpaired electrons necessary to cause this alignment in the magnetic field was just predicted by molecular orbital theory. So this is a snazzy demo that you can find online of this type of magnetism using liquid oxygen, and I totally recommend looking up the video. Like, it's super cool. Like, they pour in, literally cool, because they pour in the liquid oxygen, and liquid oxygen is blue, and then you can see it aligning in a magnetic field, and that's just awesome. I digress. Molecular orbital theory predicts this magnetism result, but you cannot get it from valence bond theory. To summarize, atomic orbitals from 2 atoms combine to form molecular orbitals, which can be expressed in a diagram which has the same number of molecular orbitals as it did contributing atomic orbitals. The energy level of molecular orbitals is determined by the degree of sp mixing, see slides 6 and 7. Ferromagnetic materials are permanent magnets. Paramagnetic materials are attracted to magnetic fields and have unpaired electrons, and diamagnetic materials are weakly repelling of electric fields, and they have all paired electrons. Bond order is determined by taking the difference between the number of bonding electrons and the number of antibonding electrons and then dividing by 2. Bond order of 0 means it won't bond.